This is Darren Pulsifer, and welcome to Rise of the Stack Developer, where the convergence of DevOps, security, and cloud-native technologies are changing the way products are developed. In this episode, we're going to talk about ElasticSearch and how to improve performance using Intel's brand new Optane DC persistent memory, and we're going to see how this works out for us. All right, first let's take a look at ElasticSearch and where we see the best uses of ElasticSearch in our data centers. If you're a sysadmin of any sort and you monitor several machines, you've probably already installed ElasticSearch and have it running where all your log files are being dumped into Elastic so that you can get a better picture of what's going on in your data center as a whole. Instead of as individual servers, you can look at them holistically across everything. It's a great tool for ingesting log files and indexing those log files. It's also a great tool for scraping public data off of like Twitter feeds or even Slack channels and combining that with other public data to get great information about what's going on in the world, maybe your customer base, whatever it is. It's also another great tool for indexing full text documents that are coming in, which it can be used in a variety of business cases. The cool thing about ElasticSearch is that the indexing that goes on also has with it a lot of other tools that allow you to visualize that data in several different ways. There's a really rich ecosystem around this, so it's a great tool. And one of the things we always are looking for is how can I ingest more data into my Elasticsearch servers and keep the response time up where I need it. Most of the time, we end up adding more servers or primarily more servers to handle the load. We find that a lot of the bottlenecks in tools like this, like Kafka is another great tool that does this, is that it uses temporary space to store these files until it gets it into a more permanent space. And that tends to be a bottleneck for a lot of things. Let's talk about how we might be able to take advantage of this new technology from Intel, which is formerly known as Apache Pass and now DC Persistent Memory. So this is really cool technology. It comes in the same form factor as your DRAM in DDR4. It's DDR4 pin compatible. It comes in 128, 256, and 512 gig modules. It's pretty affordable. Depending on the day and memory prices, it's less than half of the cost of normal DRAM, and you get quite a bit of memory with these. In fact, in a 2-socket system, you can go up to 6 terabytes of RAM using these persistent memory modules. It's highly reliable, has encryption in it, and it's pretty cool technology. Not only is it normal RAM, but it's persistent memory. So now when I turn my machine off, that memory can stay there if I set it up that way. Let's first look at how I would configure my server. If I have a 2-socket server, I'm going to primarily focus on what we call a 222 configuration, which basically means that for every DRAM module that I have, I'm going to have a persistent memory module. And in the configuration in my lab, I went with the lowest cost one, which was 16 gig DIMMs and 128 gig PIMs. So 16 gig DRAM modules and 128 gig persistent memory modules, which means I have effectively 1.5 terabytes of RAM. Pretty incredible system and really cool technology. There's other modes that you can put, you physically put the PIMs and the DIMMs together, which are right there described. So, hey, let's take a look at what I can do with this memory now. It's new technology. It's in my machine. What can I do with it? Well, there's a couple things. One is it can extend the memory that I already have at a lower price point. That's what we call memory mode. Basically, in this mode, your DRAM acts as a cache for your persistent memory, which I'm treating it like normal memory mode, so it becomes volatile memory pool. Right? The DRAM cache gives me that ability of running pretty close to the same speeds as having like all of it in DRAM, because the caching algorithms do a great job at keeping active pages in that DRAM cache layer, where less active memory is sitting out in the persistent memory pool that's there. A majority of the workloads, you're not going to see any performance difference at all. There are some where I'm evacuating the cache a lot, I'm filling up my whole cache, and where you are going to see some performance degradation, but it's not that bad. So another mode that we have is called AppDirect mode. Now this mode to me is the most exciting, because with this mode, this means that I can write programs to write directly into persistent memory. Where before I would have to write something out to a file system and, do my fopen and write it out and then bring it back in, take a data structure that I had, marshal it into a string and dump it onto a drive, or I connect it up to a database, those sorts of things. With this, I can go directly into memory. I don't have to marshal it. I just say, hey, here's a data structure, store it for me. Wow, and it's there. When my system goes down and comes back, it's there. I still have access to it. Pretty slick stuff. Now, another thing we can do in AppDirect mode is we can carve off a part of that persistent memory if we want, carve it off into AppDirect mode, and we can say, let's create a file system out of that. Now, think about this for a second. We've all done the crazy thing where we created a RAM drive, right? We took a part of our DRAM and we said we're going to make an ultra-fast drive. The only downside to that was that ultra-fast file system, as soon as my machine goes off, it's dead. It goes down and I lost all the memory. With this, it doesn't. So it's another tier of storage, ultra-fast. It goes over the DDR bus instead of the I/O bus. So it is extremely fast. So some of the tools that are out there that help you manage this new memory is, here's two of the tools that are available on the Linux kernel, and they're available in any of your modern Linux distros today. I think the first one offered was a Fedora 29. It's available on SUSE and Windows Server as well. The first command is called IPMCTL. That stands for Intel Persistent Memory Controller. This allows me, it's a utility that allows me to configure and test and monitor my persistent memory modules that are sitting in my server. So I can allocate parts of the persistent memory to go into memory mode where I'm extending my DRAM, or I can take the other part of it and put it into AppDirect mode. I can do a percentage across the sockets. There's lots of configurability there. Right? So we're going to show you some of the commands to use that. And then there's NDCTL, which is a non-volatile memory device controller. This allows me to create namespaces in that persistent memory that I've created. And I can create those namespaces in regions so that I can create them as devices, so I can easily mount them and put file systems on them. So two really important tools that we use to set up all of our testing. You can find out more about it on our blog. It gives you details on how to set it all up. Now, let's get back to Elasticsearch. When I first started looking at how am I going to test Elasticsearch and see if I get any performance gains at all here, let's see what I can do. Something interesting. So I went scouring around and looking for all the best Elasticsearch performance testing tools, and ESRally came right to the top. It's a great tool developed by the same people that developed Elasticsearch, and they have a nice metaphor that they use throughout, which is a car rally or a race. So anytime that I run a test, I run a race, and the results are stored in this races directory. I've got data that I use to run the races. That's data that I'm ingesting into my tests that I'm running. I've got teams, I've got cars, I've got tracks. And the track is your test suite that you want to run. And all this is stored in the .rally directory. Now, you can set this up to test against a cluster you already have running, against a directory where you're changing your configuration yourself, or you can have it just give me this distro and it'll download it from GitHub and put it on your machine and run it. So very cool tool, all self-contained. When I started looking at how can I use ESRally and test performance of this new ultra-fast persistent memory drive compared to like a normal SATA drive, I decided to take the easy way out. And I decided I'm just going to put the whole .rally directory on the PMEM drive, and then I'm going to put the whole thing on the SATA drive and run comparisons between the two. Pretty interesting test to do, really simple to set up, as you can imagine. Now, another thing that I did when I ran the test was I wanted to make sure that I was testing the effects of this memory drive on the performance. So I needed to get rid of network. I needed to get rid of replication of data across multiple services. I just wanted to see and isolate and see what the effects of that persistent memory drive might be compared to a SATA drive. Now, I don't have any hard drives in my lab. I just have SATA drives and now this persistent memory drive. So I can't really tell you what the results are from a hard drive. I'm guessing I know they're going to be slower for sure because spinning media just isn't as fast as a normal SATA drive or even an NVMe drive, right? So I tried to decrease the amount of variability in my tests so I can see what the effects of the drives were having directly on Elasticsearch performance. Another thing I did was when I configured my persistent memory, I configured it to be 100% AppDirect mode, and so I can mount the whole thing as file system storage. This was good for me because I easily filled up those drives. I had, because I have two sockets, it creates two regions, which gives me two file systems, each of 750 gig. And the test I'm running ran for about 10 hours, and I generated something like 1.8 terabytes of data. And it did garbage collection, did a bunch of things on there. So I filled those drives up pretty quick with the tests that I'm using there. Again, you can see the IPMCTL command is what I used to create those regions on my persistent memory. Let's get to the test results real quick. So there are tons of statistics that come out of ESRally. Oh my goodness. And understanding what they all meant took me some time to figure out. But I figured it out. And I looked at primarily, I want to look at throughput and reaction time for any operations I wanted to run on the cluster, like a search or query or indexing, things like that. So the first one I looked at was throughput. How many documents per second could I ingest into the system? And I ran it against different number of ingestion and test clients. I started with 8, 16, 32, and then 64. And if you see, the difference between 32 and 64 is pretty negligible on throughput. I actually was surprised. It started, teetering off. I didn't try 128. Maybe I'll try that next. But I started seeing this steady state. So I knew I was probably at the optimal where I wanted to get to. 32 clients seems to be optimal on throughput, on ingestion. And if you look here, I get close to a 2x performance improvement over a normal SATA drive, which is pretty incredible. Because most of the time when you're fine-tuning Elasticsearch, you're looking for double-digit percentage, not 2x. So pretty incredible performance improvement here with this persistent memory. Now, that's ingestion. Let's take a look at service response time. Now, the lower the number, the better here, because that means I'm able to respond much faster to the queries that are coming in. If you notice here, again, we're getting over a 2x performance improvement. And in fact, at 16 test clients, we're actually getting almost 4x performance. And I ran this test several times because I thought that was a little bit of an anomaly, but it turned out to be correct. Also at 32, it dips a little bit and then back up at 64. So we're getting around 2x performance improvement, and this was response time on 100% of the operations. If I decrease it down to 50% of the operations, the difference is even greater, which is pretty incredible. So call to action on this one. Go out, ask someone about DC persistent memory. This is really cool technology. We're using it as an ultra-fast file system, and we're seeing performance improvements with ElasticSearch. And if you looked at my other video, I talk about Kafka ingestion, where we're getting up to 10x performance improvement. You heard that right, 10x performance improvement, about 2 gigabytes per second per server on a Kafka cluster. So pretty incredible results. Thanks for listening to Rise of the Stack Developer. If you enjoyed our podcast, go ahead and subscribe, give us 5 stars, and let other people know. If you want more information, like tutorials, videos, white papers, check out our website, riseofthestackdev.com. Until next time, go out and build a new world, one stack at a time.